Hey, this is Vaughn Vernon. Welcome to my Design Accelerator tutorial. Today I'm talking about bottlenecks. Bottlenecks be gone. You know, in software development, there are bottlenecks everywhere. I'm going to give you several examples of potential bottlenecks and also introduce you, unless you're already familiar with it, the theory of constraints and how the theory of constraints can be used as a reasoning tool for unblocking bottlenecks and keeping them unblocked. Stay with me. I know you're going to enjoy this episode. You know, I was thinking about how many different ways software development can have bottlenecks. As I did, I made a list, and you'll notice here I think I have about 16 items so far. There are probably several more, I'm sure there are, but just consider these alone. Communication. Communication can have huge bottlenecks. Communication between the business, between software development teams, with users, with customers, with clients. Communication can really become a huge bottleneck and slow everything down. Software teams themselves can have communication problems. They can have difficulties with defects, with poor design, maybe with underperformers on the team. There can be several different kinds of bottlenecks there. Just getting requirements and understanding the requirements, understanding any kind of communication between people who have different thought processes, different ways of reasoning about problems, about solutions, about challenges that they face, just human understanding, grasping the communication in various forms, whether it's writing, human communication, through talking, direct speech, on video calls. You can have bottlenecks in programming itself, just not being able to handle the complexity. Maybe there's cognitive load in the programming or in the architectural design. A lot of different factors there. Testing the software. You can have bottlenecks whether you're doing automated testing or if you depend on some level of direct user testing, there can be bottlenecks in that area. Defect reports. Well, defect reports seem like they wouldn't be much of a bottleneck. You just simply find the defect and report it. But are the defects being reported correctly, accurately, completely? And then that ties in with defect analysis. Can you even understand what the defects are? How difficult or how easy is it to get in touch with the users or testers who reported the defects? What about fixing the defects then, once you finally understand it? And what about regression when defects are fixed? Those can cause bottlenecks. Integration between different services in software. Just trying to get the integration correct is going to cause bottlenecks many, many times. Deployment can be a bottleneck because you don't have control over a certain level of the deployment channels. And the release itself then can become a bottleneck. What if the deployment goes wrong? What if the release isn't complete? What if there's poor communication between the software development teams and those who are doing the deployments and releases? Are those a matter that are being handled by the software development teams, or is it done independently? The user experience can cause bottlenecks because they just simply don't understand. The documentation is poor or completely lacking. And then user feedback becomes a bottleneck. It's just slow. How do they get in contact with the right people? Does the information flow correctly? If business people have a direct communication with users, are they providing that feedback directly to the correct software teams, or are the defects or other poor experiences from the users being reported through the wrong channels? So the user feedback and business feedback and market feedback, all of these things can be huge bottlenecks. So think about these. What can we possibly do about alleviating the bottlenecks, about making the bottlenecks less impactful in a negative sense? How do we handle those? Let's consider. As you can see here in this example of a flow that has a bottleneck, it is representative of a bottle with elements inside that are trying to flow out, and the bottleneck prevents the flow from being the most performant that it could be, the highest level that it could be. There is a process, it's a management process, that can be used to determine what a major constraint is. In fact, it should be used to identify the highest constraint, the constraint that is leveling the worst impact on the entire process of whatever is happening at any given time. So it's known as the theory of constraints. The theory of constraints focuses on identifying and addressing the most limiting factor. Now notice, there is just one to begin with. And in fact, there is only one ever at any given time. So you are focusing on the most limiting factor, the constraint that stands in the way of achieving a goal. Now, while we're focusing on the most limiting factor, the constraint that is most limiting at a point in time, once this constraint is alleviated, you can move on to the next most limiting factor, which at the time that you're doing it becomes the most limiting factor. It was, let's say, the second most limiting factor prior to this, but once you have alleviated the initial most limiting factor, then there is yet another most limiting factor that is now highest level of constraint, the worst bottleneck situation. Now, there are 5 steps in the process for actually alleviating the constraint. So the first step is obviously identify the constraint. What is that most limiting factor, the constraint in some process that must be alleviated? Otherwise, we will not be able to achieve the goal at the most optimal level possible. So we identify the constraint. The second step is we exploit the constraint. I'll explain all of these further in a moment. The third step is we subordinate everything to the constraint. This has to do with putting your back into whatever it takes to alleviate the constraint. And then the fourth step is to elevate the constraint. This happens if the first steps aren't enough to completely unblock the constraint to the point necessary to achieve a goal. And finally, the fifth step is to prevent inertia altogether, which in essence means to repeat the process. So we're going to return to step 1, and we are going to identify now the most limiting factor that exists after the previous constraint has been identified and alleviated. When going over this list of typical software development bottlenecks, I said that there was very likely, in fact, definitely additional bottleneck types, and I did identify one more now, that is bottlenecks in runtime performance. So what I've done is provided an example problem that uses each of the steps within the theory of constraints to both uncover a problem, basically identify the constraint, exploit the constraint, subordinate everything to the constraint, elevate the constraint, and prevent inertia or repeat the process. So I'm going to go through each of these steps one by one. I have the first one highlighted here. So let's see what the constraint was that I identified. And this is an actual example from a problem that I faced some years ago as I was working on a Java bounded context that was in the healthcare industry. First of all, we noticed that there was some kind of performance issue in a heavily repeated process that caused failure of a service level agreement. So it was just taking too long to execute a particular area of code. To try to find this, I took some steps to place some time measurements in suspicious code. So I wasn't using any kind of performance analysis tool. Instead, I just went into the code and narrowed down where the problem was by placing some time snapshots and printing them out as the code ran. Very simple attempt to find the problem. The constraint was identified, and inside the constraint, the goal was basically to find one matching element within 50,000 elements total, and to return that element to the caller. The method iterates over all the elements, but does not break out of the loop when the element is found. So basically, every single time that an element was searched for, even when the element was found, the operation continued, or the iteration continued over all 50,000 elements before returning the one found item. And it could have been the second, third, or the 100th item or whatever, but we were actually iterating over all 50,000 elements. Obviously, the constraint was identified. The second step is exploit the constraint. That means to make the constraint as effective as possible. In other words, maximize throughput in some examples without significant investment. That means that you're going to use what you have at hand, make some observations, and make whatever changes you possibly can to alleviate that constraint. Now, this next part of the definition or the explanation of exploit the constraint shows how it lends itself to manufacturing. It says eliminate waste and inefficiency from the constraint operation. Well, this can be applied to software as well, but you can see how it fits into a manufacturing environment quite well. The action that I took, I inserted one line of code to break out of the loop when the element is found. Could be a return, it could be a break out of a for loop or a while loop, but the point is eliminate the inefficiency in the easiest way possible. Very straightforward in this case. So after you've done the simplest thing possible to make the constraint more effective, more efficient, the third step is to subordinate everything to the constraint. So now you're looking for even better performance. This means to align all other activities to support the maximum effectiveness of the constraint. In some cases, this might mean slowing down non-constraint operations to match the constraint's pace. In manufacturing, you might move the people involved in a manufacturing line around somewhat. Maybe you need more individuals on the constraint and less individuals before the constraint. That's just one example. In software, with a queue and reactive streams, you can use what is called back pressure. Back pressure is when the consumer tells the producer that it can only handle so many messages at a given time. That can be adjusted throughout time. Perhaps the consumer will speed up for some reason, or it will slow down for some other reason over time, and that can fluctuate. But the point is, the consumer can now tell the producer, give me only 5 elements right now. Okay, now you can give me 10 elements. You can just open it up to 100 elements. No, wait, we've gotten too much now. Back off to 5 elements again until we catch up. So that is one way to work this in software. Now, the way that I applied this in this particular case, the action that I took is I replaced the iteration over 50,000 elements to a binary search on the sorted list. Actually, it became a sorted array. With 50,000 elements, this meant that there would be a maximum of 16 probes. Now, this becomes very, very efficient. Imagine being able to use iteration of just 16 elements to find the one that you're looking for among 50,000. That's roughly what happened here. That is because a binary search halves the given array every time that it makes a probe. It takes a different slice and it basically zeroes in on the element, or it doesn't find it at all. But it knows that because it is a sorted list and it's comparing greater or lesser to the current element that you're in search of. When I took on this particular challenge, what I faced was known as time complexity. The initial problem that I faced was that the method was implemented in linear time complexity, which is commonly denoted as big O of n or just O of n. O of n means that as the input size increases, so does the processing time, and it increases proportionally. So for example, if I were to double the 50,000 elements to 100,000 elements, it would double the processing time of scanning that entire list. To overcome this, what I chose in the binary search is a big O of log n, or O of log n. which is logarithmic time. This means that even by doubling the number of elements in the array, the maximum number of probes in addition to the 16 original ones is just one single probe, meaning that it would require only 17 probes maximum to find the element that was being searched. Now, ultimately, it would be great if we could use O of 1, which is constant time. But this wasn't possible unless I were to implement some sort of index that would take care of looking up any element in the array. That would then mean, because of the index, that I would be able to find every element in exactly the same amount of time as any other element. But it really wasn't worth it. Having merely 16 probes maximum was plenty fast enough for this particular problem. Now you might be wondering, why did I not just add the binary search initially? Well, the initial problem was best handled by using step 2, exploit the constraint, because initially what we wanted to do is simply release a new version of this bounded context by fixing the major problem. That is, okay, if we had to search through all 50,000 elements and the 50,000th element is the one that we were searching for, well, we would have the worst case scenario. But many of the searches being done were resolved far sooner than that. So we were able to decrease the time required for each of the searches by simply exploiting the constraint, make that one break out of the loop or return out of the loop, and that's all that was needed at the time. We made the release, it cut down the time, that's exactly what we needed. Then, in subordinating everything to the constraint in the next step, this is where we could take an additional optimization where possible, and that's exactly what we did. Step 4 is elevate the constraint. So let's say that after steps 2 and 3, we still weren't able to maximize performance as we intended to. Well, we would then elevate the situation. As it says here, if the constraint still limits system performance after steps 2 and 3, invest in more significant changes to break the constraint. I just discussed the possibility of using O of 1, or constant time, by introducing an index. However, this was unnecessary, so we didn't have to elevate the constraint in this case. In other cases, you may well have to do so. The fifth and final step is prevent inertia, or basically repeat the process. So go back to step 1. This is emphasizing the need to avoid complacency. Immediately reevaluate and address any new constraints that emerge after addressing the previous ones. And again, just one at a time. Just one constraint at a time is what we address, but this is taking into account previous ones, plural, that you eliminated or alleviated the constraint. Now, the idea is a term that we should be familiar with in software development, ensuring continuous improvement. And I think I just demonstrated between steps 2 and 3, continuous improvement and the possibility of even more improvement in step 4, which in this case was unnecessary, but we can go back to step 1 and identify new constraints. In fact, on this very product that we were developing in Java, the bounded context, there were additional constraints in performance. One of those was a synchronous process that was operating in user time. That is, a user would perform some operation, submit some information to the server, and the server would immediately, in their user time, perform the operation, which took quite a bit of time. It could take minutes of time, which could even cause the browser to time out and the connection to the server to time out. So this meant that users were waiting on a process that blocked their progress in other responsibilities of their workflow, but it could even be somewhat disconcerting when the process seemed to completely fail. So this had to be redesigned for asynchronous processing. I used Java-based messaging to process that task and related tasks in the background. So that was yet another constraint that had to be overcome. By the way, when I say synchronous processing in user time, I'm not referring to time spent in computation in the computer outside the kernel space, as in user space, versus kernel space when you make a system call. What I'm referring to is a blocking operation that blocks the user from doing more work while the server is operating on their request. This is also known as request response cycle delay. So that's what I'm referring to when I say user time. In this tutorial, I chose to dive into runtime performance as the bottleneck or constraint to understand how to alleviate. In future tutorials, I'll dive into domain-driven design, team topologies, DevOps, CI/CD, or continuous integration, continuous delivery to alleviate some of these other bottlenecks or constraints. I look forward to that in the future, and until next time, take care.